Okay, so we're now looking at lab 20, part 3.2, and here's the circuit we've wired up, and we're going to see what happens as we increase the frequency. So we've done this with the analog discovery kit, and it needs only 5 volts. So here is ground. This is the other, this black wire is the other ground. This red wire is our plus 5 volt supply from the analog discovery board. This yellow wire is our signal generator. So it's a square wave coming out of the waveform generator. And here's a 10K resistor. It's connected to the gate. So we have gate drain source on this N-channel MOSFET. Well, you probably hear Alfie. You see there's Alfie wondering what's going on. Oh, who's a good boy? Yeah. Okay. And gate drain source. Now the source is wired directly to ground, and the drain in the middle has a pair of 100 ohm resistors going up to plus 5 volts. So I made an intermediate stop there, and then this red wire goes up to plus 5 volts. And okay, so now you can see, let's see, I'll go over to, where is it? Oh, WaveGen, okay. So we have a 100 hertz square wave, and it's amplitude 2.5 volts, offset 2.5 volts. So it's going back and forth between 0 volts and 5 volts. And then, oh right, in power supplies, we have the positive 5 volts on. And then in oscilloscope, we're watching what's happening. So both traces are 1 volt per division, and we have 2 milliseconds per division horizontally. And I put in an offset of minus 3 volts, just so you can see the full range of 0 volts up to plus 5 volts clearly. And so yellow is, that's the orange wire here, which is at the gate, and blue is at the drain. That's channel 2. Okay, so the yellow trace is the orange wire. It's channel 1 of the scope. It's looking at the gate, so that's switching the MOSFET on and off. And then the blue wire is looking at the drain. So when the MOSFET is off, as you can see when the gate is down at 0, then there's no current flowing through the MOSFET. So there's no current flowing through the pair of 100 ohm resistors. So the point the scope is looking at, which is where the drain is, which is right below the 100 ohm resistors. So the scope channel 2 is looking right here. It's looking at this point. So if the MOSFET is off, then this point will just be at 5 volts. If the MOSFET is on, then this point will be down close to 0 volts, because you have 50 ohms of resistance here, and you have a very small on resistance of the MOSFET down here. So for one thing, it's interesting to see just how close to 0 this gets when the MOSFET is on, because it tells you something about the on resistance of the MOSFET. And it looks like it gets pretty close to 0, so I guess the on resistance must be much, much smaller than 50 ohms. And okay, so this works well at 100 hertz. So now, and you just see that when the MOSFET is on, the drain is, MOSFET is on, the drain is low. When the MOSFET is off, the drain is high. So that works just the way you'd expect a perfect switch to work. Now, let's go over to Mr. WaveGen here, waveform generator. And we'll go up to, let's go up to 500 hertz. And then we'll go over to Mr. Scope here, and we'll just change the time base. So you can see, okay, same thing but faster. So let's change the time base to 0.5 millisecond per division. Now, okay, so you see, actually this is the gate. So you see the gate, there's a little seems like there's some gate capacitance. There's a little RC time constant as we charge up the gate capacitance. So you can see that the gate no longer slams straight up from 0 to 5 volts. It actually takes a little while to charge up the gate. And then there's this little glitch here. We'll see that become more prominent in a moment. And then meanwhile, okay, here's the drain. So when the MOSFET is on and when the MOSFET is off. Now let's go up even a little higher in frequency. So let's go up to like 2 kilohertz. And then we'll go back here. And let me just zoom in a little bit on the time scale. Okay, so now you can see that it takes a little while to charge up the gate, and also you can see there are 2 time constants here. So it looks like there's a relatively small gate capacitance, and then something qualitatively different happens here for a while, and then there's a larger gate capacitance. And I think what's happening here, actually this is known as the Miller plateau or the gate plateau in turning on a MOSFET. And actually I think I linked in the lab handout to a paper describing this effect. But I think essentially what's happening is as a bunch of charge is attracted to the region of the gate from inside the bulk of the MOSFET to form the channel, the conduction channel, then as that conduction channel forms, the gate capacitance increases. Because I guess you could argue, I think my naive argument is, you know, a capacitor is like dielectric constant times area divided by distance. And so if you imagine that you bring some conducting layer of charge closer to the gate, then you should increase the capacitance. So I think that makes sense to me. You've got a bigger capacitance when the channel is formed than before the channel is formed. If you find a reason either to confirm or refute that argument or improve it, let me know. Anyway, so we see that there's some limit to how quickly we can switch this at high frequency. We can even go up to slightly higher frequency. It starts to peter out, but if we go up to 5 kilohertz here, then I think that's already enough to see it not work too well. And if Tom suggests we go up even a little higher in frequency, so what the heck, let's try 20 kilohertz. I'm pretty sure this will fail. Yes, and then it never quite turns on. Okay. So now what should be interesting, I'm going to just make another video of what happens when I replace the 10K resistor. Now if you want to make it go faster, then there's some time constant RC. C is fixed by the MOSFET. So I guess we'll do a lower resistor, a smaller resistor to make a smaller RC time constant. So I'm going to start a new video after swapping out that resistor for a smaller resistor, and we'll see what happens here.